Hi class. We're going to do lesson 69 and 70 by video because we weren't in class on Thursday and I wouldn't want you to miss geometry. So lesson 69 is about trapezoids and kites. The first thing that we can look at is a typical trapezoid. A trapezoid will have one set of parallel lines. We can mark that as parallel. And it's going to have two other lines that aren't necessarily going to be be parallel or congruent. But we do have some terminology for trapezoids. This is going to be the base of the trapezoid, which is going to just be the bottom line. So if I flipped it upside down, then this would be the base. Okay. The base angle is going to be the angle that is formed by the base and one of the legs. We have two base angles in a trapezoid, and then the legs are going to be the non-parallel sides. So in this case, in Q, R, S, T, we have angle T and angle S are the base angles. We have QT and RS as the legs. TS is a base and QR is the upper base. Okay, with trapezoids, we have an interesting thing that takes place in Theorem 69.1, and that is the mid-segment of a trapezoid. So when I connect the midpoint of one leg to the midpoint of another leg, I end up with another parallel line that is parallel to both bases and that has a length that is equal to 1/2 the sum of the two bases. So in this case, let's call this U and this V. So in this case, we're going to write this. UV is going to be equal to 1/2 the sum of QR plus TS. It's very interesting because if I know one of these or two of these, I can always solve for the third one. So it's an interesting relationship. So let's go ahead and look at this in terms of numbers. Let's make a trapezoid and then put some numbers to it. So here I have my trapezoid, A, B, C, D. My lower base is 30 inches, my upper base is 12 inches, and I'd like to figure out, we can call this EF, what is the length of EF? So using this theorem, 69.1, the EF is going to be equal to 1/2 the sum of 12 plus 30 inches. So that will be 1/2 the sum of 42, and EF then is going to be equal to 21. So we have 12 inches on the top, 21 inches in the middle, and 30 inches on the bottom. Interesting. Well, we can have a special kind of trapezoid called an isosceles trapezoid that we can do some more things with. So that would be a trapezoid in which not only are the bases parallel, but the legs are actually congruent. And that also means, since the legs are going to be congruent, these base angles are also going to be congruent as well to each other, not all four of them. So base angles, so if I call this A, B, C, D, that means my base angles A and B are congruent, and my base angles D and C are also congruent. And then that leads us to be able to make some other interesting conjectures and to be able to solve for some different angles and sides and that sort of thing. So let's make our shape more interesting by turning it on its side and saying that since I've marked these as congruent and these as parallel, that I have an isosceles trapezoid. So let's say that this angle here is 118 degrees, then I can determine all of the other angles in my isosceles triangle. Since I said it's an isosceles triangle, then you should know that these two bases are going to be congruent. So that would make this one also 118 degrees. Since this is a quadrilateral, it has to have a total interior sum of 360 degrees. So if I take 118 times 2, I get 236. If I subtract that from 360, I get 4, 4, 2, 1. I get 124. That means that each of these is going to be half of 124, which will be 62. Another thing that I could have done to figure this out is that because these two are parallel lines, this line that cuts through it is actually a transversal, which makes these same side interior angles, which also makes them supplementary. So I could have taken the route of just saying these two have to be equal to 180 degrees as well. So two ways that we can look at that. Okay, another property of an isosceles trapezoid is that we can say something about the diagonals. Since these angles are congruent, the diagonals of an isosceles trapezoid are also congruent. So that leads us to be able to solve some more interesting problems as well. So again, if this is A, B, C, D, AC will be congruent to BD. So let's look at another isosceles trapezoid. This time we're going to turn it upside down a little bit, make it look different. Okay. So A, B, C, D, we'll call that intersection E. So let's say I would like to find I'd like to find BE. So I'd like to find this right here, okay? If I know that AC is equal to 18.5 centimeters. I also know that AC, AC, let's make that so you can read it. You see that? So AC, and I know that EC is equal to 4.2 centimeters. Okay. All right, well, if I know that AC is equal to BD, correct? And I know that AC is equal to 18.5 centimeters. So that means that BD is also equal to 18.5 centimeters, which means that I can take this portion here and say this is going to be equal to here. Another way that I can look at that is because I know this is an isosceles triangle, I can go ahead and set this up as showing that these are two congruent triangles. I mean, since this side is congruent to this side, and then I know that my base is equal to my base, I can also show that because I have congruent base angles on each of these, and that my diagonals are cutting them at the same ratio, I can go ahead and set up two congruent triangles. But to simplify matters, we'll just go ahead and use our the properties of an isosceles triangle and say that if this whole thing is 18.5 and this small part here is 4.2, the whole thing is 18.5, then I should be able to take 18.5 minus 4.2 and say that this portion here is 14.3, which means that this portion also has to be 14.3 in order to make these two congruent. So just another way that we can use the properties of an isosceles trapezoid. Okay, well, let's look at a kite for a moment. A kite is an interesting figure because, let's see here. Okay, a kite is going to have two congruent sides here and two congruent sides here. So these are adjacent sides that are congruent. It also has another property in that the diagonals are perpendicular to one another. Excuse me. So let's say that I have this kite and, well, I'm supposed to draw a different kite. My kite looks different on my paper. So let's look at this kite. And I say that this little segment here is 4, this segment is 4, this segment here is 7, and this little segment here is 3. And I would like to know the length of all of the sides here. Well, because I know that the diagonals are perpendicular, then I can say that I have a whole bunch of right triangles in here, which means that I can use the Pythagorean theorem on all of these things. So this one should be obvious. If I have this one right here that has legs of 3 and 4, that means my diagonal is going to have to be 5, right? Because it's a triple. So these are each going to be 5. And then here I have another right triangle. Sorry. I have another right triangle here, which is 4 and 7. And so I just have to use the Pythagorean theorem to figure out what what my hypotenuse is. So that would give me, what can I write? 4 squared plus 7 squared is equal to the hypotenuse squared. So 16 plus 49 equals the hypotenuse squared, which is equal to 4, 5, 65 is equal to the hypotenuse squared. So the hypotenuse is going to be the square root of 65. So this would be the square root of 65. So that means that this side is the square root of 65, this is the square root of 65, and each of these are 5. So, and this comes out to about 8.1, just so you know. Okay, so those are all the different ways that we can utilize the properties of trapezoids and of kites. So your homework for this lesson, I would like you to do the odd problems in lesson 69 plus number 14. And that will take care of your kites and your trapezoids. And then I'm going to go ahead and make the next one for lesson 70. And then we'll pick up then with the investigation on Monday. So have a good weekend.